Let's take a look at this configuration, which is called a summing amplifier. And so if we look at the configuration, we notice that it's actually just a variation of our inverting amplifier, where we have more than one input on our inverting terminal. So it's just a variation of inverting amp, except now instead of just having the R1, we have also R2 and R3. In order to aid our analysis, we can label some currents. Again, we can feel free to do these any direction we want. We just need to keep in mind our passive sign convention. So let's draw I1, I2, I3 through resistors R1, R2, and R3 respectively. And let's also define some current over here. Let's just call that I. I'm also going to label this point at our inverting terminal as A, and that's just going to let us identify that a little easier when we're referencing things here. Okay, so if we're going to analyze this circuit, and again our goal here is to get a general expression just like with our other configurations, we can start with the two sort of basic ideas of our ideal op-amp. So remember, the first, or one of the ideal principles of our op-amp, is we have zero current coming into our op-amp terminals. So we have zero current coming in here and here. So what that means is if we do a KCL at node A, we just have the four currents that we just defined in blue there. So let's do KCL, Kirchhoff's current law, at point or node A. And what we get from that is I1 plus I2 plus I3. Those are all of our currents coming in, and that equals our current coming out, which is I. And so we know this because we have zero current into an ideal op-amp. Okay. So our other property of our ideal op-amps that we want to use is that the differential input voltage is zero. And so we can write that as VD, our differential input voltage, is equal to zero. And so what that means, and this is for our ideal op-amp, I should write. And so what that means is our inverting and non-inverting terminals are going to be at the same potential. So the way we have it here, that means our inverting terminal is going to be at a virtual ground. So inverting terminal at virtual ground. And so since we've labeled that A, we could also say voltage at A, V sub A, is equal to 0. So what that means then is we can explicitly define our voltages across all of these resistors if we wanted to. We could say, for instance, here is V1, since over on this right side is ground. Here is V2, here is V3, and then across RF we have our voltage V out. And so again, that's just because at point A there we have a virtual ground. So now what we can do is we can use Ohm's law to get each of those currents in terms of the voltages. So for instance, our I1 is just going to be V1 over R1. So I1 equals V1 over R1. Similarly, our I2 is just going to be V2 over R2. Our I3 is going to be V3 over R3. And then finally, our I is going to be equal to negative V out over RF. And so the reason we have this negative sign is of course because of passive sign convention. If we come back up here and we look at this, we see our reference current I is going through a voltage rise. So we fall into that otherwise category for our passive sign convention, which means we need a negative sign in any equation relating current and voltage. So now what we're going to do is we're going to take these expressions for our currents right here, and we're going to substitute them back up into our initial KCL equation. And from there we can solve for our relationship between our output voltage and our various input voltages, V1, V2, and V3. So a little different again from previous circuits because now we have multiple inputs. Okay, so let's do that. So if we substitute in, of course what we're going to have, we just have V1 over R1 for I1 plus V2 over R2 plus V3 over R3, and that's going to be equal to negative V0 over RF. And so of course to solve for what we want to get our V0 on one side and our inputs on the other. So we can multiply through by that RF on both sides and distribute that negative as well. So we can think about it as multiplying through by negative RF. If we do that, what we'll get is V0 is equal to negative. Now we're going to have V1 times RF divided by R1 plus V2 times RF divided by R2 plus V3 times RF divided by R3. And so that would be our generalized equation for this particular circuit. And so we see it's satisfying our gain because we have our output over there on the left and our various inputs on the right being multiplied by certain constant values. And so what we notice if we look at this is that our output is a weighted sum of our inputs. So output is weighted sum of inputs. And we notice that it's also still inverting our input because we have that negative sign out front. And so we're going to see a useful practical application of that in a later video where we talk about using this type of circuit as a digital to analog converter. A simple one, but one that works pretty effectively. So let's say maybe for this circuit we only had two inputs, V1 and V2, or maybe we had 5 inputs. So how would our equation change? Well, if we want, we can go ahead and just look at the form of this equation boxed in red and generalize that. So that way we can deal with it if we have even more inputs or fewer inputs. So let's say we want to generalize the equation above. And so what that's going to look like is we would say V out is equal to negative the sum from I equals 1 to n, so we're talking about n inputs, of Vi times Rf divided by Ri. Okay, so let's box this equation in too, because that's a useful one if we were talking about a more general situation. And of course here we're talking about n inputs, and of course Vi goes with Ri. And so what that means goes with, we could also say it's in series with. For instance, of course, V1, if we come back up here, V1 is going to go with R1 in the equation, V2 is going to go with R2, and so on. So that's our good generalized equation there. What we're going to see in the next video is an example of the summing amplifier, and we'll also analyze some powers before moving on to look at even more configurations.